Um, in this project, essentially, you will be looking at the, remember, when you have the risky asset and risk free. Yeah? And when you only have those two assets together, you mix them together, and we call Y was the weight of the risky asset. And we call the risky asset, we call it P, right? Remember that convention that we had? So you will choose the weights, and based on that, you will figure out, given the expected returns of P, the risk of P, and the risk-free rate, you will mix those two assets together using some weights, and you'll figure out all the possible levels of returns and risk that you can obtain. So you will create this graph right here. But that's pretty easy. Expected return of C, which is the combination of the two, as a function of weight. So it's going to start at risk-free. This is the expected return, and it's going to get to here. Yep. So you have to recreate that graph. What is the mathematics that links the returns? It's the weighted average of the returns, right? So here C is equal to Y, here P, plus 1 minus Y, risk free. So this is how much you invest in P, this is how much you invest in the other asset. Yeah? Then you're gonna do the same thing for risk. So what is the formula for risk? You can see, well, the risk of C is just Y sigma P. And so you will, at 0, you start here, and then, I don't know, you get to sigma P. Then after that, we worried about utility. So out of those infinite portfolios that you can create, which one is the best for a specific investor? Well, you ended up with this other graph that links weight and utility. And what is the formula for utility? Is the expected return of the portfolio minus 1/2 A sigma C squared. Yeah. So you will use this to figure out what the RC is. You will use this one to figure out what sigma C is. Then you're going to put those two numbers together into this one and calculate utility. So the value, the graph of utility is going to look like, depending on what values you have, it's going to look like something like this. So what is the ideal portfolio for this guy? It's the one that is at the peak, right? It's the one that provides the highest utility. And how do we call the asset allocation that generates that? What was the symbol that we used?
Y star.
It was the Y star. So remember, in class we said, this Y star, you can actually calculate it analytically. And what was the formula for it? That? Yeah. So in class you could calculate that, but here we are not doing calculations. Here we are actually graphically we want to see what the peak of this thing is going to be. Now, what is the challenge that you will have in doing this project? Well, I don't want you to create a bunch of graphs. I only want you to create one. So you have to put all this stuff together in a single graph. So your graph is going to have 3 things: 0, 1, Y. You have the expected return of C. Then you have the risk of C, which can be something like that. And then on a secondary axis, I want you to give me the utility. And so this graph is going to look like So you're gonna have some practical problems, some practical challenges in figuring out how to put this stuff together. The most difficult thing to deal with is that most likely the value, the scale of risk is going to be much larger than the scale of expected returns. So this is going to be something that goes, say, perhaps from 0.001 to 0.004, but this one is going to go from 0 to 0.2 or 0.4. So how can you make this thing fit in a graph, given that the scales are so different? But if you put them in the same graph, then this line is going to look like flat, or probably it's going to be squashed all the way to the to the x-axis. So we want to make sure that those things are visible. So to accomplish that, instead of plotting sigma c, I will plot sigma c divided by some number divided by 10. And then you write it here. This is not sigma c, sigma c divided by 10. So what I did here is 1/10 of the actual value of risk. If I want to know what the actual value is, I'll multiply it by 10 to get the real value. Okay, so this is one of the challenges that you will have. Then the next thing would be, what if you allow shorting to take place? So if you allow shorting, then y can take a value that is greater than 1. But essentially it's just a redo of all this thing with y greater than 1. Okay. So let's try it out. So you're going to look at your existing data collection. And so the table that you're creating for project 1, you looked at several ETFs, right? And pick one of them. Make sure that the expected return has a positive value, otherwise things are weird. So you have a choice between several of them. And copy the expected returns on your portfolio. Copy here the standard deviation for your ETF, and then you have your risk-free rate. Yeah, so those are numbers that you have now. Let's suppose that your expected return was 0.1%, so 0.001. Your standard deviation perhaps was 0.2, so high. And the risk-free rate, the directions tell you that the risk-free rate is 1%. Remember, the data you collected is what, daily, weekly, or monthly? I don't remember.
I thought it was weekly.
It was weekly. So the APR, the risk-free rate I'm giving you, look up the number, but I believe it's 1%. The risk-free rate is 1%, yeah. So this is an APR. You have to convert that to the same scale as the returns that you have. So you have to convert that to weekly. How do you convert that to weekly? You have to divide it by how many weeks in a year? 52. So take that number divided by 52. So the risk-free rate is going to be equals to 0.01 divided by 52. Yeah? Okay, so make sure this is an important step, otherwise your plot is going to look like this number is going to be up there and this one is going to be lower. Alright, so once you've done that, you'll need the coefficient to risk aversion, okay? And I'm going to pick a number there, I suppose it's 5. And now I can start working and create the different weights, y, 1 minus y. And then here we'll calculate the expected return of the combined portfolio. And here calculate the standard deviation of the combined portfolio. Yeah? I don't know this plus sign here. Once I have those two pieces of information, I can calculate the utility. So those are values that I get to pick. I'm gonna test all possible weights, or of course a subset of that, discrete set of them. And then from there, the rest is gonna be computed. Now, to make things easier, instead of calling this cell C4, which can be meaningless, let's give it a name. So you click on the cell, then you click here in this little window, and you say, I want to give this thing a name. The name is gonna be underscore big E R P. Okay, ERP. So every time I want to refer to that cell, C4, I just have to type underscore ERP. Yeah? So, what about this one? Well, I'm gonna give it a name, underscore. And the reason why I put an underscore is because if you just put letters and numbers, Excel may get confused thinking that you're dealing with a column in a cell. So it's easier if you put the underscore symbol in it somewhere. So I'm gonna call this standard deviation of P. There it is. And again, I still can type it. Yep. Then this I'm gonna call it underscore risk-free rate, and this underscore A. And I messed it up. There it is. Underscore A. Yep. Got it? Have you ever done this in some of your classes where you can actually define a constant? Yeah. So this is very useful because when you write the formula, it's going to make much more sense, and it's easier to troubleshoot. All right. So I want to recreate this graph. So the values of y start at 0, arrive to 1. So 0. Eventually I need to get all the way to 1. You want to make sure that this graph is somewhat smooth, right? So you don't want to pick numbers that are very far apart from each other. I would pick these plus 0.005, and there it is. So those are going to be all my weights. Start from 0 all the way down to 1. Yep. So if this is the weight of P, what is the weight of the risk-free asset? Well, it's going to be 1 minus the weight of the other one. So this is going to be equals 1 minus this weight. And add it. So one way to make sure that you didn't screw up, highlight a random cell. I mean 2 random cells, one next to the other. Their sum should be 1, right? And if you highlight all of them, the average should be what? 1.5, right? Half and half. All right. So now I need to calculate the expected return of C. So this is going to be equal to, let's see, it's y, the expected return of P. So this is going to be my y times, what do we call the expected return of P? Underscore. And there it is. So the user-defined cells already pop out. That guy. Plus 1 minus y is this cell right here, times the risk-free rate. We call that underscore risk-free rate. That's it. So copy and paste it down. So let's see if it makes sense. If I invest nothing in the risky asset, I'm essentially investing everything in the risk-free asset, so the weight of my portfolio is going to be the same as the risk-free rate. What should happen here? What should I get? I'm only investing in the risky assets, so I should get this number right here. Yeah? Let's try. Worked. So this is supposed to be the standard deviation of P, so it's your formula there. It's equal to y times how do we call this guy? Underscore standard deviation key. So let's see. I'm investing only in the risk-free asset, so my risk is 0. And down here, I'm investing only on the risky asset, so my standard deviation should be 2.2. Let's see if it works. Yeah. Next, I need to calculate the utility. So utility is the expected return minus 1/2 A sigma squared. So the expected return is right here. Minus 1/2 is what? 0.5 times coefficient of risk aversion, which I called underscore A, times, divided by times sigma squared. That didn't quite work. So this is the portfolio I'm evaluating, right? So this guy squared. So how should they really look like? What if, depending on what the value A is, it should perhaps increase and then maybe start decreasing after a bit. So let's see. So yeah, it starts at some number and of course decreases all the time because I go wrong. Let me leave it. Oh, because those are numbers I made up, of course, that's why. Alright. Did I screw up somewhere? Expected return minus 1/2 A squared. Does it understand the order operations? There was a version of Excel that didn't quite understand powers. Did they fix that? Yeah, they fixed it. Okay. So, how do we graph this thing? Go to insert, and then chart, scatter plot. And whatever Excel is thinking about doing is probably stupid. This case actually predicted things almost correctly. But let's start from scratch. So you go to select data, and let's remove everything. And my first series is going to be the expected return. So I'm going to call it year C. Then you have the X values. You want to plot everything as a function of Y. And then what are the Y values? Those guys right here. Okay. So check it, the graph looks right. And then, okay, then add a new one. This is the risk. And this is what things may look weird. So the X value is always going to be the same. The only thing that changes is the Y values. And there it is. What's the problem? It's a scaling issue, right? This is the orange is much larger set of values than the blue. So how can I force this thing to be on the same axis? On the same graph. I can just redefine, for graphing purposes, a new variable called standard deviation divided by 10. So if I divide this by 10, this number is still going to be too big. So maybe about divided by 100. There should be somewhat comparable. So it's equal to that divided by 100. So I don't know what kind of standard deviations you're going to have in your data set. So you'll have to play with the numbers so that this graph looks acceptable. So you see that they are, this number can coexist with this one on the same graph without distorting the graph. So I'm going to click on this guy, select data, and I'm going to edit it. And instead of plotting the standard deviation itself, I'm going to plot the standard deviation divided by 100. So this is not standard deviation anymore. This is going to be standard deviation divided by another. Yeah. So now the two graphs can coexist in the same plot. What about utility? Well, utility might have a really weird scale. So I don't want to put it with this. I want to still add it to this graph, but I'm going to send it to a different y-axis. So add utility. The x values are the y's. The y values are the utility values. And there it is. So again, messed everything up. So you click on the utility graph, right click on it, and I forgot. Format data series again? There it is. Format data series, and then go on the secondary axis. So the values of utility, you now read them in here. Then of course put the labels and all that stuff, but essentially this is the graph I want you to come up with. Questions?
Do you want the standard deviation, whatever number we divided by, listed on there?
Yeah, just when you make sure you put the labels for the y-axis, labels for the secondary axis, and there is an legend here. So on the x-axis, you shouldn't say, what is this? This is the weight of B. Right? So label it, put the title. Those are little details that they're not much fun. Questions about this? Can you handle it? Yeah. So, well, clearly this is not a major exercise in Excel. I mean, this is stuff that you, it's not particularly instructional for your level. We want to do this for a practical purpose. I want to see graphically what happens if you change investors, somebody who's much more risk averse than this guy. So the question is, what happened to the utility? And what happened to the optimal portfolio if the investor is more risk averse? What do you think is going to happen?
It's going to go closer to the risk free.
So to make him more risk averse, this number will have to be higher. Yeah. And if I make this number higher, the peak is going to move closer to the y-axis, and the height is probably going to shrink. Let's see. See the scale has changed? The peak has moved a little bit to the left. It's hard to tell, but that's pretty much what happened. What if I make the investor less risk averse? So let's put a 20 here. The peak is somewhere around there. See that the scale has increased to the 10. And keep going like that. I mean, this all depends with your the data that you have. Okay. So the curve is becoming a bit flatter. And now you can see that it's kind of peaking up here. Yeah. Questions? So what if I want you to plot the point that has the highest utility? Well, one way to do it is use the maximum function and say, give me the number that has the highest value here. And so 0.0274, this is it. And so you can identify this point and change its color on the chart. Just change that particular dot. Okay. Questions? So if you look at the second page of the handout, the third page shows you the graph that I want you to create. And now what if borrowing is allowed? What if you can short? Well, how do things change? I'm gonna have to add the borrowing rate here. And so this is gonna be equals to, what is it, 3%? So 3 divided by 52. 3 divided by 52. And I'm gonna call these, guess what? Underscore borrowing rate. How can I handle that? Well, in the case of borrowing, you're not limited to a weight of 1, you're limited to a weight that is bigger than 1. So what is the maximum there? 1.3. So take this guy and extend it until 1.3. The problem is that at this point, the composition of your portfolio is no longer the T-bills MP, but it's going to be the loan MP. So when you calculate the expected return, it's going to be these times the return of P plus 1 minus Y times the borrowing rate. So this is the difference. What the heck is that? RB? I called it RB, right?
It's a BR.
BR. Why didn't pick up the name?
No.
Okay, fine. Borrowing rate. Why? It's because I didn't press enter. That's what I did. So there you are. Yeah. So put the formula like that. This one is going to be the same thing. Still uses standard deviation, does not have returns. So drag it down. Utility is still calculated the same way. Drag it down. And this is for plotting purposes. So then create a different graph for the borrowing case. And so I'm lazy, so I'm not going to do that. I'm just going to change those, edit, and drag it down. This one is this guy. This is so exciting. Alright, and then utility. So just make a copy of this graph and then modify it. So, see what is happening to the expected returns? There is a kink on the curve, and the same thing is happening here. It does not, although it's not very visible. This is a curve, but then here there is a sudden change into that. So if I increase the borrowing rate to a higher number, those things are going to be a bit more pronounced. And that's it. So what I want you to do is, using your real numbers from your data set, I want you to start messing with this A. And don't expect those your numbers to be these. I think the one that worked was 5 for when I did this project with real values. But change this number, and I want you to change it so that the weight that generates the optimal portfolio is specific values. So one question that you have is, what value aim will make the investor better off by borrowing? So that means, to what should I change A so that the peak falls here, this range after the king? And so what do you think? What should I do with A? Make it larger or smaller? Smaller, right? You need to be more risk tolerant or less risk averse. So 1.05. See, the peak is now there, and the peak is not visible, but you know the deal. So you cannot even see the curve part anymore. But that's pretty much what you need to do. Mess with that, and then answer the questions. So you need to do the graph first, and then answer the questions. Play with the numbers. Then you can always double check things by using the actual formula, right? You know how to calculate the peak analytically, so you can use these questions. So I think this project is easier than the other one. The calculation part is pretty straightforward. The skill to remember is that you can name cells. And there is also another way to troubleshoot things. Like, suppose I want to make sure, I want to kind of figure out what the numbers, where the numbers are coming from to generate this value. If you go to formulas, you can do trace precedence, and this tells you what are the inputs of this cell, where are they coming from. It's getting a number from here, a number from here, a number from here. So there is a quick way to see where the things are going. Alternatively, if I want to know who's using this number, you do trace dependence, and this tells you that this cell is used in here and there. Okay, so those are things that can help you in making sense of an Excel spreadsheet. Questions? Have you ever used those tools before? Yes? Good. So if you haven't, then practice them. You good? How long do you think it's going to take you? Like an hour, maybe? So, yeah, we did it in 40 minutes, and I spent half an hour trying to log in. So, all right. Questions? No questions?
It says due Friday, October 14th. Is that meant to be Monday or?
What is October 14th? Is that a Monday?
It is Monday.
Yeah, it's a Monday.
Okay.
Yeah. You can always turn it in earlier if you want to. You know, like this one. I can check it for you, and it's perfectly fine. So try to get as many points as possible on this project. Yeah. All right. Say bye to them. What did we do last time? So we identified what the first of all, what kind of scenario were we working with?
Sorry, we're working with two risky assets.
Two risky assets. All right. And we said when we're dealing with two risky assets, how do you calculate? What are the different levels of expected returns that you can get? Because well, that's big. The weight of one of the two assets, we call that equity and debt. And the way you calculate the expected return of P is the weight of equity, expected return of equity, weight of debt, expected return of debt. Yeah, where weight of debt is 1 minus the weight of equity. So using these, we said the levels of expected returns that you can get is linear. And it ranges between those two extremes. Then we say, what about risk? And well, there things are more complicated because the risk of the portfolio is the weight of equity. I forgot. You should have memorized
Yes,
this.
weight of equity times the, whatever the sigma of equity squared.
Sigma E squared plus
Weight of debt.
weight of debt
Sigma debt.
squared plus twice
Plus equity.
the weights times the covariance between the two. And then the square root. Where the covariance is what is the risk of debt, the risk of equity, correlation between debt and equity. Yep. So depending on what the level of correlation is, the graph of risk can take different forms. All forms, you start from this, and you end at, depending on what scale this is, but this is the risk of equity. And if the correlation between the two is 1, then this graph looks like that. If it's -1, you get something like this. And anywhere in between, you get something that looks like a curve. Yeah, so the lower the correlation, the more picture grabbing this thing at some point and pulling it down. Yeah. So then last time we said, well, let's suppose I'm an investor and I'm concerned with risk. I would like to figure out if I can find a portfolio that has the lowest possible risk. So we said, weight of equity that produces the portfolio with the smallest risk. And so the way we did it, we took this formula right here, took the derivative, set it equal to 0, and so for the weight. And ultimately we ended up with this one right here. I think it's sigma d squared there. I don't remember, I need to look it up. Yeah, I got it right. So I said, remember to try to be able to recognize these. In the exam, I'm gonna give you some of the formulas. This is one of the ones you'll be given. And so what is this thing telling you? Well, given the characteristics of DNA and how the DNA correlate with each other, so where this curve is equal to sigma d, sigma e, correlation. Yeah? So given the characteristics of the two assets, this tells you that unique way that you can mix them and get a portfolio that has the smallest amount of risk. Yep. You good? So let's do a quick application here, example. Consider the following assets. Equity, debt, expected return, So given this, I want you to construct the portfolio with the smallest risk. Okay, and you have $84,000 available. Yeah, $84,000 available. So how do we do it?
Plug those values into the.
So you know the characteristics of the two assets. You know the formula that gives you the weight of the portfolio with the smallest risk. Yep, and then plug the values. So the easiest way to do this thing is directly from the table. From the table, calculate the values for sigma squared and put it in there. And then calculate the covariance. So that you can substitute numbers more easily there. So what is this? This is 24 squared, which is what?
576
576. What are the units?
percent squared.
This symbol squared, whatever that means. The other one is 12 squared is 144. Symbol squared. Yep. And then what about the covariance? The covariance will be 24 symbol times 12 symbol times 0, which is 0. So essentially now you have another subset of inputs. You can directly put them in here. So sigma D is 144 minus 0 divided by 144 plus 576 minus 2 times 0. So what do you get? Oh, so I forgot one thing. Forgot the units, right? So the units here are symbol squared, symbol squared, symbol squared. So you get 144 symbol squared divided by 580, 627.20. Symbol squared, and then symbol squared and symbol squared cancel each other out. So your answer is already in the correct units. What do you get?
Point two.
0.2. Do you agree with that? Yeah. So how much do you have to invest in each asset? So this means that the weight of equity in dollar terms is going to be just the weight of equity times the wealth or the value of the portfolio, which is 0.2 times $84,000, and that's 16,800. Is that correct? Yep. So how much you have to invest in that? Well, it's either 1 minus 0.2 times 84,000, or just take the 84,000, subtract this from it, and you get the amount. So what do you get? So 84,000 times 0.8.
67,200.
67.2. Yep. Does this make sense? Questions?
I'm not getting 144% and 576%. I'm
So-
getting 1.4.
Oh, it's because you converted that to decimal, right?
The percentage?
Yeah, you did this 0.12.
No, I left them as percents, but I'm getting 5.76 and 1.44 when I square them in Excel.
Because Excel is converting that to decimal. Yeah. So it shows you the percentage. So, but Excel can't figure out what's going on with the percentage square.
Okay.
It's something that I've added as percentage square because I don't want to convert to decimals multiple times and deal with the very tiny numbers.
Okay.
So I just leave it as a symbol, that's fine. Yeah, so think of a percentage as, I was supposed to divide by 100, but I haven't done it.
Yeah.
And think of it that way. So if you forget to divide by 100, but also you forget to multiply by 100, then the answer is correct, right? And so that's pretty much the idea there. Questions? So what if I asked you, what is the level of risk of this portfolio? How would you do it? I want to know, what is the risk of this portfolio?
You use a formula for risk of the portfolio.
So you use this one with what numbers? What weights?
The optimal weights.
Yeah.
The weights are just calculated, right? So if I want to know the actual location of this thing, so far I figure out that is somewhere in here, is actually at 0.2. But if I want to know where this curve reaches its lowest, I have to evaluate that at 0.2. Yeah? So be careful with the way the questions are being posed. Sometimes I want to know the weights, sometimes I want to know the actual value of risk. Questions? So, where are we gonna go with this thing? Let's suppose, I think we got here last time, and that's where we stopped. This is 0, 1, weight of equity. And let's focus on risk here. Oh, I'm sorry. One is right here. So this is my risk of debt, risk of equity, and this is my same graph but with the returns. So this is expected return of debt. Expected return of equity. So this is the location of the smallest risk. I just call the W min. I don't know, can't come up with a better name. This is the sigma p min, the smallest amount of risk. You agree with that? So we calculated this weight by using this formula. We will calculate the value of this risk using those inputs into this one. And so this is something that we can figure out. Now, as an investor, if you wanted to be exposed to this much risk, then you have two different ways to achieve that, yeah? If I want this much risk, I can either use this weight or this weight. Remember last time we did a problem like that? So let's translate those weights into this other graph right here. So this is equivalent of A. Let's call this M, like minimum. And this is the other number, right? So what's the difference between point A and B?
Returns, expected returns.
The risk is the same. So the weight of equity A is such that the risk of the portfolio A is equal to the risk of the portfolio in B, but this is generated by the weight of equity at B. This is the weight of equity at A, weight of equity B. Do you agree with that? So two different ways to generate portfolios that are identical from the point of view of risk. But what about these in terms of returns? Well, the expected return of A, the expected return of the portfolio at A, the expected return of the portfolio at B, they're different. In fact, the expected return of at A is less than this one over here. So notice that I picked 2 points at random here. Well, this is true for anything that is away from this portfolio over here. So as an investor, what set of portfolios would you pick? The ones generated on this half of the graph or this other half? To the right or to the left?
Right.
So let's think, what is the reasoning here? For any level of risk that I choose, I have two possible asset allocations. Of those two asset allocations, one of them produces returns that are lower than the returns of the other asset allocation. So if I have to pick between A and B, I will always pick the one that is on the right end of the graph. Okay. So of all the possible weights, the weights of equity that are greater than the weight of equity that produces the minimum variance are better than the weights of equity that are below the weight of equity that produces the minimum variance. So those are better and those are worse. Yep. Does it make sense? So even though there is a continuous range of possible weights that go from 0 to 1, it turns out that the ones that investors would prefer are the ones that go from this weight that produces the minimum risk portfolio up. So there is a subset of weights that are better than the rest. Does it make sense? Questions? So remember that the reason why we're doing this is to figure out if we can match the ideal portfolio for a specific investor given the investor's preferences. And the way we did that stuff was find the best portfolio for an investor. And the way we did it last time, we said, well, we dealt with graph that had expected returns on the y-axis, risk on the on the x-axis, and those curves, how do we call those? They produce the same level of utility
Indifference curves.
in different curves. So if I give you selected portfolios in this graph, you would use the indifference curves to figure out the portfolio selection, right? So we need to do the same thing here. We want to figure out what is the best portfolio for an investor in this setting. We are dealing with two risky assets. The problem is that this graph is risk as a function of weight, and this graph is expected returns as a function of weight. The universe of indifference curves is expected returns as a function of risk. So how can we change this graph into that? If you remember, we did the same thing for the risky and risk-free asset, and we said those were some type of parametric equations. Essentially, you pick a weight, you identify a point for sigma p, a point for ERP, and you trace it there. And then you pick another weight, and so forth. So if you do the same thing, where you have expected returns of p here, sigma p here, pick the weight of equity to be 0. What do you get? If the weight of equity is 0, you get ERD and sigma d. So you get this point. Like that. Then pick WE to be 1. So you get another point. You get here E, sigma E. So this is you investing only in D, this is you investing only in E. And then if you pick values that are in between, let's suppose you pick this WE min, or the one that produces the smallest risk, then what would you get? Well, you get the sigma P min and some number for the expected returns that is between those two extremes, right? So what is the characteristic of this? Well, this is a number that is below sigma D and sigma E. So it's a number that is somewhere to the left of that, and in terms of expected returns is somewhere in the middle between the two. So it's somewhere around here perhaps. So this is gonna be your sigma min. So what is the only way to connect those points? Let's suppose that you pick intermediate weights and you calculate all those things. This increases linearly with weight. This first decreases, reaches a minimum, and then increases. So if you start from here and increase the weight, for every incremental weight that you pick, you're moving up a little. You're moving up, following this slope. But in terms of risk, your risk decreases first and then starts to increase. So you're moving up, decrease first. Then once you reach this point, increase the weight of equity, what happens? Your returns keep increasing, but your risk also keeps increasing. So that's how this graph looks like. Okay. So those are 3 important points of the graph. Yep. Questions? What if correlation is lower than this? whatever this correlation was. What do you think is gonna happen? Well, if correlation is lower, this graph gets lower, it's more stretched down. So the level of risk you can achieve is even lower than this. This means that if that is stretched down, this is stretched closer to the y-axis. Yeah? So if correlation is exactly -1, how would this graph look like? If correlation is -1, you can actually find a weight where the risk is 0. So if correlation is -1, this would kind of look like this. Touches here and then bounces back. I mean, that look awful, but it looks like that. Yep. What if correlation is exactly 1? If correlation is exactly 1, you have a straight line. So picture this being less and less sloped down. This is less curved. So if correlation is +1, look at this. So that's how the graph looks like. Questions? So in the exam, what kind of question can I ask you? I can ask you, show the relationship between the risk of P as a function of the weight of equity. So think about what I'm asking. I want the two words that I'm using in the question is what I want on the y-axis and what I want on the x-axis. So if I ask you the question, I want this graph. If I ask you, show me the relationship between the expected return of P and the risk of P, I want this graph. So what are the weights in here? Well, the weights are not shown directly, they are implicit by each location on this graph. So let's think about that. D, E, minimum variance, suppose I have this portfolio right here. So I have portfolio X. How could I rebalance my portfolio so that sigma P is equal to sigma P min? So what should I do? Should I transfer money from D to E or from E to D?
D to E.
So let's see. How do you achieve this portfolio right here? What is the weight that allows you to achieve that? How much am I investing in equity here?
0.
I'm only investing in D, right? So the weight of equity is 0. What about here?
1.
In order for me to have a portfolio that is identical to E, that means I'm investing only in equity and nothing on that. So the weight of equity here is 1. So can you tell me what is the trend that takes you from this point to that point?
Increasing the weight.
You are increasing the weight in equity little by little. So if you have this portfolio right here, you have this portfolio X, and you want to get this one, what should you do? Invest more in equity and less in debt. So as you rebalance your portfolio, you're essentially kind of walking along this curve. The more you invest in equity, the more you walk to the right. The more you invest in debt, the more you walk towards this point right here. Got it? So let's see if we can figure out what is the best possible portfolio for this investor. We have this scenario. So this is when you invest all in that. Okay, no. sigma D, sigma E, your D, and your E. Yeah. Is it time? What time is it?
Oh, it's,
215.
Okay. So this is the minimum risk. And now let's pick the indifference curves of this investor. So you have portfolio A, A prime, B, B prime, and C. What is the relationship between A and A prime?
they're the same utility.
Yes,
I was gonna say it is 216.
16.
Yes.
All the time.
I heard that I had 16 more minutes.
Oh, now it's 216.
Okay, I was feeling very like, oh my god, I can't take this shit anymore. Much longer than 16 minutes. So I will figure that stuff out. We'll do it on that.
What are you doing after this? What are you doing after this?
So when I say,
What are you doing
is
after
there,
this?
do I have time? Just say
Eating?
no.
Eating? I'll go to the library. Before.
I have a question
I'm gonna
super
go
quick
touch up on
if
project.
you.
What project?
This one?
Oh.
So, I got this far and there is no expected shortfall.
I'm gonna go print
No,
one out.
because it's the one that I.
Ethan, I'm gonna go print one out in color.
There you go. I might, well, I'm gonna ask him in a sec.
Yes,
I don't need
he said,
Oh yeah, check it out. I got my charger for
He
it.
showed me. I
It
was
works.
like, that's crazy. The
It works.
TI-84 plus.
I stole it from my sister.
It is hot.
That's why it's pink.